Hello, my name is Mohsen Sayadi. Today I will talk about our new research about detection of novel social bots by ensembles of specialized classifiers on Twitter. Nowadays we use social media for different aspects of our life. Unfortunately, there are some automated accounts on social media with many purposes. Some of them are malicious bots who try to spread misinformation. So automatic bot detection on social networks like Twitter is a mandatory task. Unfortunately, the adversarial setting of bot detection problem makes the classification of these accounts in the wild hard because bots try to change themselves to evade bot detection. Researchers proposed automatic bot detection methods falling in two main categories: network-based and feature-based. Network-based methods analyze the whole network around the accounts and do the predictions. But feature-based approach includes supervised learning methods in which they compute features based on an individual account, and then they do the prediction based on those computed features. There are some limitations of for supervised learning bot detection methods. For example, they're not suitable for coordinated bots, for identifying coordinated bots, because these bots look normal individually, and we need to analyze them in a group to understand that they are automated. On the other hand, unsupervised learning methods are suitable for finding these kind of bots. Uh, the key limitations of the key limitation of supervised bot detection methods is that their performance drops in cross-domain when we test them on new types of bots that are not similar with the bots in our training set. This limitation was mentioned in the literature. For example, Echevarria mentioned that even a classifier trained on over 1 million accounts, including 22 class of bots, was unable to identify new class of bots. Another example of supervised learning method is BOTOMETER. It is the first publicly available bot detection tool on Twitter. BOTOMETER employs 1209 features, and it uses a random forest with 100 underlying decision trees. The output of BOTOMETER is a bot score between 0 and 1. A bot score close to 0 means that the account is likely to be a human, and close to 1 means that probably it's a bot. The cross-domain prediction performance of BOTOMETER has been criticized in the literature. For example, here we see an automated account on Twitter that generates lines of a famous novel, and we see that BOTOMETER recognizes this account as a human. We will focus on limitations of BOTOMETER in the wild in cross-domain experiments in this paper, and we try to improve it. We use some labeled data set in our experiments. Some of them were used in the training set of BOTOMETER, and some of them are used for cross-domain experiments. Some of them actually were used in the literature to criticize BOTOMETER. Let's see a simple example of a cross-domain bot detection. We trained a logistic regression on Carolee using the top 2 important features that discriminates bots and human in this dataset. We see that the linear classifier can fairly separate 2 classes when tested in the same dataset. But if we use the same rule and the same set of features on a new dataset, which includes new types of bot, the performance drops, and we are not successful in separating 2 classes. Why? Because bots are different, and we need a new set of features and new set of rules. We investigated the diversity of bot classes, and we understood that different bot classes have class-specific behaviors. For example, bot class like fake followers, who who are bots that they follow a lot of people and they hope that people will follow back. Their top feature is friend-follower ratio because they follow a lot of people and not all of those people follow back. So at the end, they have large values for that feature. Let's see more examples of cross-domain classification and compare precision and recall. In the diagonal cells, we present the in-domain experiments. For example, here we train on Cavalli and we test on Cavalli. And we see that the numbers are larger or better compared to the cross-domain experiments shown in the non-diagonal cells. And we also see that recall drops more in cross-domain experiments compared to precision. We justify in this way because we miss identifying new types of bots in the new data set. But the bots that we can find, and we say that it's a bot, we're probably right. So let's investigate more around cross-domain experiments, and let's see at the density of bot scores for bots and humans. Again, we see in domain experiments, the separation is impressive. For humans, it is left skewed. For bots, it is right skewed. And if we define a threshold around 0.5, we get a good accuracy or F1. But in the cross-domain experiments, we see something interesting. For humans, majority of the cases, the density for bot scores is left skewed. But for bots, majority of the cases, it is not right skewed as we wanted. Why? Because humans are more homogeneous in cross data sets compared to bots. So that's the second empirical findings. Based on the two empirical findings that we found, one, diversity of bots, second, humans are more homogeneous, we proposed a new method, ensemble of specialized classifiers, ESC. We train different classifiers for different class of bots, and we train one classifier random forest for humans. And we take the most confident score at the end as the final bot score. Note that for RF0, human specialized classifier, we use 1 minus bot score because for humans, closer to 0 means that the bot score is more confident. We tested ESC and compared ESC with BOTOMETER version 3 and TweetBot 2, and another famous bot detection tool that is publicly available. We also included BOTOMETER version 3.1, which actually uses the same method as BOTOMETER version 3, but with a revisited set of features. We tested on 6 left-out data sets. We combined those data sets, and we see that on the combined test set, ESC can beat all of the baselines. In the paper, we presented that in details on 6 left-out data sets, and in all of them, BOTOMETER version 4 could beat BOTOMETER version 3, which means that in cross-domain experiments, ESC generalizes better. Another advantage of ESC is that when we feed the same amount of accounts from new domain, when new class of bots appear, ESC adapts more quickly and learns faster. Why? Because base classifiers in ESC, they work independently. When we get a new class of bots, we train a new specialized classifier, and that classifier specifically works on like 50 examples. But that's not the case for BOTOMETER version 3, which has only one random forest. In light of the experiments, we employed ESC in BOTOMETER version 4 and launched BOTOMETER version 4 recently with new features. We report bot type scores, which brings more transparency. So users can understand that the final bot score is coming from which specialized classifier. Despite the new challenges, we fight with manipulations on social media with novel ideas. Thank you.